Let's get started. Happy Valentine's Day, everyone. So today we're going to finish up Naive Bayes and we'll review it again quickly and talk about a few extra Naive Bayes details, and then we will cover decision trees. And that should get you through most of what you need for homework 3. I think by the end of this week, you'll have everything you need for homework 3, or possibly by next Tuesday, but you have kind of an absurdly long time to do it based on the poll. So I think that should be nice. But then homework 4 deadline might be coming up only a couple weeks after that. So I wanted to start by just zooming back a little bit and talking about where we are in terms of classification. So far in this class, we've been covering exclusively supervised learning algorithms. And within supervised learning, there's regression and classification. But you could also divide up supervised learning by parametric and non-parametric learning. So let's formalize that difference. So parametric learning is where we learn model parameters, hence the name parametric. So learn model parameters, and examples of that, well, IE is wrong, it should be EG. Examples of that include linear regression and logistic regression. As well as neural networks, which we learned last time are a generalization of linear and logistic regression, in which we will go into much more details of later in the class. And then we started talking about non-parametric learning algorithms, where we don't learn parameters. So models that don't learn parameters. And the two examples that we've covered so far are k-nearest neighbors and naive Bayes, and decision trees, which we saw briefly in the coding and which we'll start talking about today as well. So k-nearest neighbors, pretty simple, probably the simplest learning algorithm we've learned in this class. And then we started talking about naive Bayes, so I want to quickly review what we've covered so far and formalize some of the things that we didn't cover. So naive Bayes uses Bayes' rule, one of those probability rules, where the probability of the label given the data is equal to Bayes' rule, and where X is the label, Y is the label, X is the data. And to classify, this is all review, but to classify, we evaluate the probability that Y is equal to a certain label, given that X is equal to the input data point for all possible labels. And we choose the label with the highest probability. So choose label with the maximum probability. And then we noted that in practice, the probability of x denominator doesn't make a difference. So we don't bother calculating it. And just to see that, if we were trying to predict dog versus cat, and we have probability using Bayes' rule, we'd look at probability of the data given that y equals dog times the probability of dog divided by the probability of x, and we'd compare that to the probability of our data given that y equals cat times the probability of cat divided by the probability of x. And we're dividing by probability of x both cases, so we could kind of just ignore that denominator. It doesn't make a big difference in which one of these is higher. And this is a common theme in machine learning where we kind of simplify what we're comparing when it doesn't make a difference, because ultimately we're just trying to see which class is higher. So kind of a recurring theme. We've seen it with maximum likelihood. We've seen it in some other contexts, but same denominator. So can ignore. And just a note on homework 3. Homework 3. And so in the homework, it says only calculate the numerator. This is what we mean. So this is what homework 3 means when it says only calculate the numerator. So sorry, I'm going through this quickly, but that's just because it's all review from last class. So we also talked about the conditional independence assumption. So let's formalize that again using the conditional independence assumption. We could say that the probability of our data is equal to feature 1, feature 2, feature 3, and feature 4, given, and this is where the conditional and conditional independence comes in, given the class that we're evaluating is equal to the probability of feature 1 given the class times the probability of feature 2 given the class times the probability of feature 3 given the class times the probability of feature 4 given the class times, well, sorry, that's Bayes' rule. So for example, if 4 features, then the probability, the numerator of naive Bayes is the probability of x given y.
Is that capital X or lowercase x?
Doesn't matter too much in this case, but technically it would be capital.
It's including the base of the matrix.
Yeah, exactly.
Sorry, just to clarify, when you say conditional independence, you mean like independence depending on y?
1 second, I'll take questions in a second. Times probability of x2 given dog times probability of x3 given dog times probability of x4 given dog times the probability of dog. So this evaluates to this using the conditional independence. So conditional independence means that if we're conditioning on something, in this case, conditioning on y, then each of those probabilities are independent given y. So it's not that x1 is independent of x2 in all cases, it's that x1 is independent of x2, assuming that y is true. And that's the assumption we make. And remember, independence of probabilities means that you can just multiply them from our probability rules. Yes?
Are you saying that this is always true, or are you saying that you assume that this is true?
So we're assuming so naive Bayes assumes conditional independence. And so this is true assuming conditional independence.
Okay, so, okay.
Yeah, basically what it says. And so the training, so that's to classify, and just multiply out the probabilities and see which one's higher. But to train, and I'm putting train in quotes because it's not really training in the case of parametric learning, but all we do is pre-compute the probabilities. And so in homework 3, when you implement the dot fit method, you're pre-computing all the relevant probabilities. And then when you call the dot predict method, what that's doing under the hood, what you'll implement is doing the multiplication and seeing which one is higher. So let's just practice this one more time, because this is where we ended last class. So let me give you a slightly different table, and I'll just use 5 data points in this example. So 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 0, and 1, 0, 1, 0. And let's say we're predicting car versus bike. And we're kind of we're not really specifying what the features mean, but you might, x1 might be presence of 2 wheels, true or false. x2 might be color is red, things like that. So, the probabilities we need are, first we need the probability of each class by itself. So anyone tell me what's the probability of car from this data set?
3 over 5.
3 over.
50%.
Yeah, all correct. What about probability that y equals bike? Shout it out.
2 over 5.
Okay. What about probability of x1 given car?
One over 3,
And why is it 1 over 3?
because the car is given and we only choose the each one.
Yeah, so given that it's a car, that leaves us with only 3 possibilities. One of them has the value x1 equals 1. So how about probability of x1 given bike?
1.
Okay. We'll just do a couple more. Probability of x2 given car and probability of x2 given bike. So let's start with x2 given car. 1 over 3, good. And what about x2 given bike? Okay, cool. So you could keep going, and now you have all the relevant probabilities so that when you classify, you multiply them out in the correct way, see which one is larger. that's basically where we ended last class. Any questions on this? So you're implementing this in the homework? Okay, cool. So a couple other new things about naive Bayes, one of which is important for the homework. So one potential problem with this method is that what if probability of xi given y is equal to 0, which means that there is no examples where given that it's bike xi is 1. Well, when we're multiplying out the probabilities, we'd have a 0 for that feature. So we'd have probability of x1 given y times dot 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 times 0 times dot 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 times probability of xn given y times probability of y. That's what we calculate, and that comes out to be 0. So no matter what all the other probabilities are, if you have 1 0 probability in there, it makes the whole thing 0. And it might just be that there's, let's say you're doing spam classification. What if there's just a new word in the email? Are you just going to predict it as not spam just because there's a word that didn't appear in the training set? Doesn't quite make sense. So a 0 occurrence just completely breaks all of this. So the fix that people use to avoid this, and this is something that you'll implement in the homework via smoothing parameter, which is one of those things you have to fill in. So the fix is called Laplacian smoothing, which sounds kind of complicated from the name, but it's really not. The idea is simply that you add 1 to the numerator of all probabilities, and you add the number of classes. So in spam versus not spam, that would be 2 to the denominator. So, yeah, I mean, that's basically it. So
in this case, would it be like car and bike?
what do you mean?
So like number of classes, I guess I'm just confused if classes refer to the features or just the type of bikes that we have.
Yeah, so classes are the categories that you predict. It's
Okay.
another word for categories that you predict.
Okay.
So yeah, I guess we might not have referred to it as classes before. This is a common,
Like the spam or no spam, the number of classes is 2.
yes, exactly. So, number of output. Yeah, class is, hence the name classification. You're predicting classes. Class can mean category in regular English as well. For example, let's say that we're predicting between 3 things. So example, predict between, okay, I'm going back to health just so I'm not thinking too much about the examples. No cancer, kind of cancer, I'm not sure if that's a real thing, and cancer, so 3-way, then, actually, sorry, that's not, let's just go back to spam. This is not gonna work. So let's do spam, kinda spam. Not, and definitely not spam. Maybe it shouldn't be kind of, maybe it should be maybe spam.
Practice it might be might actually be suspicious because Google will say stuff I think is spam or not spam, though it might put suspicious.
Yeah, so let's, like, what would be a rare word that you might not encounter a lot?
Ostrich.
Ostrich, sure. Is that how you spell ostrich?
No, O-S-T-R-I-C-H.
That's how I would spell it.
Even rare.
Makes it more suspicious.
Yeah. Ostrich given y would be 1 over oh, sorry, let me write this out. Given y, so we'd evaluate these for each condition of y. So let's say given that y equals spam would be equal to 0 plus 1 over the total number of spam emails plus 3.
Wait, that's what I'm confused about, I guess. So the denominator, why would you take just the spam emails and not all emails?
Because this is given spam. This is the probability given spam. So similarly, the probability of ostrich given that y is equal to maybe spam would be 0 plus 1 over the number of maybe spam plus 3, etc. So connecting this to homework 3, in homework 3, well, actually one more thing before that. We'll connect it. So you could have a general variation of this, and this is what actually you do in homework 3. So a common variation is to use a smoothing parameter, which we'll call beta. So then so in this case, you're adding that smoothing parameter to the numerator instead of just 1 to the numerator. So it basically tells you how much to smooth, and you adding that parameter times the number of classes to the denominator. So then you could actually, hyperparameters are more correct. Using a smoothing hyperparameter where you add beta to the numerator, or add beta times the number of classes to the denominator. And in homework 3, beta is the smoothing parameter. Technically hyperparameter. Okay, any questions on smoothing? Okay. One other practical consideration that I'm not making you implement in the homework, but in every real world implementation of naive Bayes, it's implemented. Again, you're welcome for not making it as complicated as the real world, is underflow. And we've had underflow in the past when we've been looking at maximum likelihood estimation. So a practical consideration, and this is one of those other recurring themes in machine learning. Underflow, when you multiply a lot of probabilities together, So like 0.00000000000 .003 would just be represented as 0 on a computer. So just like with maximum likelihood estimation, the standard fix is to maximize the log of the probabilities. So for example, recall that log of AB equals log of A plus log of B, and this is definitely review. Then maximizing probability that the probability that we look at in naive Bayes that y is equal to any class given the data is the same as maximizing the log of that probability. Or in other words, the y value that's the max is going to be the same if you take the log. So writing that out, we take the log of the naive Bayes equation. Now I'm just going to write it out in a general form. So this is the multiplication symbol, where we take the probability of feature I for class J. This is just another way of writing what we were doing before, just more mathematically formally, given the class times the probability, well, let's be specific. So that summation is, or sorry, that product is over just that times the probability of y at the end. So the log of that is equal to the sum over each of the probabilities, the sum of those same probabilities plus, oh sorry, I forgot the log, equals the sum over those probabilities of the log of that plus the log of the last probability. And so instead of calculating all those probabilities multiplied together, you just sum the log of all the probabilities. This is just the math way of writing that. In homework 3, you don't have to do this because we're only looking at 3 features. And so if you multiply 3 probabilities together, it's not going to underflow. So for homework 3, it's okay. In the real world, if you're not just looking at the presence of 3 words, you're looking at the presence of a dictionary of words, tens of thousands or hundreds of thousands of words. So if you multiply tens of thousands or hundreds of thousands of probabilities, that will underflow for sure. Wait, here, and then here.
Is that supposed to be J equals 1 to D?
Yes. Yeah.
I don't understand what this has got to do with what you wrote on top of the underflow.
Oh, so
What has that got to do with the log?
So basically this statement, maximizing the probability is the same as maximizing the log of the probability. And therefore, the log rule allows us to add everything up. And when you add things, it's not going to underflow because you're doing addition rather than multiplying. So think about 0.01 times 0.01. All of a sudden you have 0.0001. If you do that type of multiplication for tens of thousands of words, you're going to have a lot of zeros. And computers can't represent that. So they just represent it as 0. And then you lose the probability.
Oh, okay.
Yep.
Question?
Yeah.
So, for question 5, if our, if it's off by a couple of decimal points, is that a big deal?
Um,
Cause like it's, this, my answers are the same up to like, I don't know, like I have 0.0937579298265664 instead of 6566.
why don't we take a look at that during office hours?
Okay, I'm sorry. I'm just wondering if that was gonna be. That's not like resolving to everything, but.
It depends. Basically, it depends on whether your calculation is right or if that difference in decimal is due to an incorrect calculation.
Okay.
Um,
Sorry, I'm just.
Not needed for homework 3, specifically the log stuff. But this is always needed in the real world. Or more generally, when the number of features is large, which would be the case in actual spam, no spam classification, where you're evaluating many words and multiplying each of those probabilities. Okay, so that's basically it for naive Bayes. Any questions on naive Bayes? Does everyone feel confident about doing this on the homework?
I just have a general question. Is
Yep.
there a scenario where we would prefer to multiply rather than take logs?
If you wanted the actual probability, you could multiply and divide by the p of x as well. No one actually does that though, because again, it underflows, and so people just accept they're not gonna get the actual probability. And if you're not gonna get the actual probability anyways, because you're taking the logs, you can, well, I guess you can do the
undo
e
it,
to,
right?
yeah, so I guess you could undo it, but people don't require the actual probability. Also, it's not a great estimate, because it makes a lot of assumptions, specifically the conditional independence assumption, which is usually not the case. Usually there is correlation between features, between inputs to the model, and we will learn about that more in detail, including in homework 4, which is themed on, largely on feature correlations and things like that. Okay, so we have a lot of learning algorithms down now. We have linear regression, logistic regression, k-nearest neighbors, naive Bayes. Ready for your 5th learning algorithm? Okay, new learning algorithm, decision trees. And I guess we kind of saw this during one of the coding notebooks, but we're gonna go into much more details on decision trees. So, decision trees, and these can be used for classification or regression. We'll start by talking about classification. It's actually not too different to use decision trees for regression either. So let's say we want to build, let's go on this cat-dog example, and in general build a animal decision tree. Which has a few, whoa. I think I might be becoming dyslexic based on, okay, so has wings, which, yeah, they might not have wings, they might have wings, and if they have wings, then we can go ahead and classify it as a bird and be done. If it doesn't have wings, then we might look at a second feature. Yep, there we go again. Which is the length being greater than 3 feet. And if no, then we can predict a mouse. And if yes, then we can predict snake. So this would be 3-way classification with 2 input features. And we can see that decision trees are pretty simple to interpret. You can explain how to use a decision tree model to probably anyone in your family over 5 years old. And so that's a nice benefit of decision trees. They're super easy to use. And you know, the prediction with the decision tree, just go down the tree until you reach a leaf node. Training's a little bit more complex. So let's look at training. So training, there's many variants to how to train a decision tree, first of all. We're not going to talk about all of them, but the general idea is to recursively, actually let me pause there. Who knows about recursion from CS? Who doesn't know what I'm talking about when I say recursion and recursive function? Couple. Okay. I won't make you implement any recursive functions in this class, although that would be interesting homework, maybe next year. Well, actually, no, recursion's kind of hard to implement. But basically, it's where you solve sub-problems in the same way as the as the main problem. So you break it down. So in this case, we recursively split the tree on variables. Well, let me be more specific than variables. On features, on input features. They're always input features in the context of machine learning. On input features with the largest, quote, information gain, which is kind of abstract right now. And in this definition, I'm using it abstractly. Information gain also happens to be a quantitative technical metric, which we'll also learn about. But here I'm using it loosely as the general concept of information gain, which is still kind of abstract. So let's draw it out. So when I say high information gain, which is good in general in life, it's good to gain information. Then let's say we have a node that can be split in this way, and our data set has 5 of the green X categories and 5 of the red circle categories. High information gain would be when we split, we do a pretty good job of separating the categories. So we're gaining a lot of information about how these categories differ with respect to that variable that we're splitting on. So that's good. In contrast, low information gain, which is bad, just in general in life, but also in machine learning, would be this type of scenario where, again, we have our 5 X's and 5 O's, and when we split them, we don't really, actually, for this example, I'm going to do 6 because it illustrates the point even better. We don't really get much information about how the class that we're trying to predict differs. So this is a bad split. It's low information gain. We split on that variable. It doesn't really tell us much about how the two categories differ. So that's kind of the high level idea. Now let me go ahead and give you one of the algorithms for decision trees, and then we'll break it down, go through an example, and hopefully through that process, it will be elucidated how decision trees work. So a basic decision tree algorithm, is called ID3. Happens to stand for iterative dichotomizer 3. Kind of a cool name, not really important that that's the name, other than if you create new machine learning algorithms, you could kind of name them whatever you want. So they name this
Where did
ID3.
3 come from?
I assume it's the 3rd iteration of their iterative dichotomizer algorithm that they made. So let's go through the steps of this algorithm. First abstractly and then with an example, and I think we've seen in this class when we do the example it all becomes clear. But first, let's just list the steps. I think that happened with gradient descent and also with naive Bayes. So we take a data set D and a set of features. Set of features F. So the first step is to calculate the value of a splitting metric. We'll talk about possible splitting metrics. Of possible splitting metrics for every feature F, which is in our set of features of data set D. So we look at each of the features, the inputs to the model, and calculate our splitting metric on each of those. Step 2, trying to see if I should draw anything or go straight to an example. Step 2 is to split the data set D into subsets based on the splitting metric. We'll cover specific splitting metrics in a second. Then we make a node for the selected feature F, which either minimizes which minimizes or maximizes the metric. And then step 4, we recurse using recursion on the subsets using the non-selected features. So at a high level, we calculate a splitting metric, which tells us the information gain. We split the data set into subsets based on the information gain for each feature, and then the one which minimizes or maximizes our information gain or information gain like metric, we will then split the data set into parts and do the same thing on each of those parts. But now with all of the features that are remaining, because you've already split on the feature above, and you do the same process again, recursively on each of the children. Do y'all know what I mean when I say child node feature? Okay. So I know not everyone here is a computer scientist, but has everyone taken like the intro ICS classes? Anyone has not? Okay. I'll try to cover it in a inclusive way. But I think maybe the next thing to do.
Question.
Sure.
When you say minimizes or maximizes, is there like a condition that we want?
Yeah, so we'll get to that. But there's, and actually, to answer your question, there's many possible splitting metrics. And we'll talk about a few. But before I can go to an example, let me just cover one of them, which happens to be popular. So, semicolon. One popular one is called Gini impurity. Which is what we'll use to work through our example, although in the homework you'll use a different one. So Gini impurity can be defined as 1 minus the sum over the classes of the probability of each class squared. So K here is the number of classes, and P sub I is the probability of being in class I. So in the case of Gini impurity, we split on the lowest impurity, which is in contrast to some other metrics where conceptually we'd want to split on the highest of those metrics. So to get a little bit of intuition as to why this is a good metric, let's look at an example of high impurity and low impurity. So high impurity, the maximum impurity is when you have the same probability for each class. And let's say in binary classification, that would mean we'd have 1 minus the probability squared minus the probability of the other class squared, which 0.5 squared happens to be 0.25. 0.25, so 1 minus 0.25 minus 0.25 equals 0.5. So let's contrast this with low impurity so we can see how this metric behaves differently in a low impurity situation. So low impurity situation would mean having high probability for one class and a low probability for the other. So for example, this might be in binary classification 1 minus 0.99, probability of 0.99 for one class, and the probability of 0.01 for the other class. So 0.99 squared happens to be 0.9801, and 0.01 squared happens to be 0.0001. So this comes out to be 0.0198. So what we see is that when we have a good split, or the split which would result in a high probability of one class and a low probability for the other, the Gini impurity gives us a low value relative to a high impurity situation where it's going to give us a much higher value. And mathematically, the reason this works is that if you have a midpoint probability like 0.5 and you square it, it's going to give less extreme values when you square it, like 0.25, versus if you have one of your maximal possible probabilities, which when you square it could give you a much higher number that's much more than twice as high as what happens when you square the midpoint probability. And so therefore, if you subtract this really large number from 1, it's going to be, the square of it's going to be much greater than the square of this smaller number. It's kind of a similar intuition to mean square error, where when you square it, it makes larger numbers explode and grow in magnitude, versus if you don't square it, if you do mean absolute error, MAE, then you don't get this effect. So that's precisely why we square it. But really, all that we really care about in these metrics is that it gives us one value when you have similar probabilities and a different value when one class has high probability and the other has low probability. So Gini impurity is one metric that satisfies that property. And you could create your own decision tree metric that satisfies those properties. So there's no reason you have to use Gini impurity. This is a formula that happens to satisfy the property that we care about. It's a general thing in engineering. You don't have to do things how I teach it to you. Just know what the constraints and what the properties are, and then use something that satisfies those properties. So this is just an example of something that satisfies those properties. Let's look at an example, and I think this will make all of this much more clear, as usual. So we're gonna do an example of a decision tree construction process, and we're gonna use Gini impurity as our splitting metric. As our metric. So let's say we're trying to do hurricane classification. So let's say we have one feature is it rainy? Another feature, which is it humid? Another feature, which is what's the temperature? Which is it a hurricane? Yes or no? See, no, not a healthcare example, and still interesting. So gonna fill this out. So Y means yes. So we might have one data point, yes, 7, not a hurricane. Yes, no, 12. And the temperature is in abstract units, by the way. No, yes, 18. Yes. No, yes, 35. Yes. Yes. yes, 38 is a hurricane. Yes, no, 50, not a hurricane. And finally, no, no, 83, not a hurricane. So that's our data set, and we want to find out what would be a good decision tree. So we're going to use the ID3 algorithm with Gini impurity as our splitting metric. So the first step, we want to see which input has the lowest impurity. So we're going to evaluate each of these one at a time, starting with rainy. So if we split our data by rainy, so we're basically saying, let's say that we did choose rainy as our first variable that we're splitting on. What would happen? What would be our impurity if we had done that? So we want to look at the value that we're predicting, hurricane, given that it is rainy and given that it's not rainy. So when it is rainy, and think about this in terms of naive Bayes, given that it's rainy, the hurricane, so let's see, rainy is these top two examples and the second to last and third to last example. So out of those four, there's one example where hurricane is yes, and 3 where hurricane is no. So one of those examples had hurricane yes, and 3 of them had hurricane no. And similarly, when hurricane is no, when rainy is no, so that would be row 3 and 4 and 7. So out of those 3, 2 of them have hurricane is yes and 1 has hurricane no. And so we can calculate the Gini impurity for each of these. So the Gini impurity for hurricane is equal to yes, is using our formula from above, 1 minus the probability of it being a hurricane given that it is rainy. Minus hurricane being no. And this happens to evaluate to 0.375. We can do the same thing for hurricane is equal to no. So 1 minus, now we're looking at the hurricane equals no. So we have 2/3 for hurricane equals yes. And 1/3 for hurricane equals no. It happens to give us that value. And the total Gini impurity is going to be a weighted average of hurricane equal yes and hurricane equals no. So if we're looking at of rain equals yes, rain equals no. So that would be 4/4 plus 3 times 0.375 plus 3/4 plus 3 of 0.444 and that equals 0.405. So we have a metric that roughly means the opposite of information gain, opposite direction of information gain, and it's and we calculated that when we split on Rainy. So we got those numbers using the formula above. We now do it for our.
Sorry, I'm confused. How do you split? Why do you split on rating?
We're splitting on each of the possible inputs and comparing their Gini impurity. So we just split on Rainy. Now we're going to do the same thing on humid. And don't worry, we're not going to evaluate it with as much detail as we did for Rainy. But same thing. Now we're saying, okay, that's what would happen if we had split on Rainy. Now let's see what would happen if we split on humid. So again, we look at how the hurricane outcome variable is different when we split on humid this time to see if maybe humid would be a better split instead. So, using the same logic as before, we get 3 yeses and no 1 no in this case, and we get 0 yeses and 3 nos. So already we might be thinking just humid might be a better split because in one of the split it gives us unanimous hurricane being no. So we could stop there. But if you had done all the work for calculating the total Gini impurity, it would happen to come out to 0.214, which again, we want the lowest Gini impurity. Notice that that's lower than 0.405, so seems to be working out. Finally, we're going to do this on temperature. And temperature is a little different than the first two because the first two are categorical variables, yes or no. Temperature is a continuous variable. So what we do in this case is we want to look at just the temperature with respect to hurricane columns. And we're going to calculate many Gini impurities. So just copying over that part of our data set. 7, 12, 18, 35, 38, 50, 83. We had no, yes, 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 no, no. So what we want to do is look at the average value between each of these numbers. So average between 7 and 12 is 9.5. Average between 12 and 18 is 15, etc., etc., etc. And for each of these, we want to calculate the Gini impurity, which I'll just give you the answers and then I'll work out one of these for you, just to not be super repetitive. So this is what the Gini impurities happen to be. And then I'll show you how to do it for the continuous variable case. Obviously, when I say you, I mean the program that you write to create a decision tree. So what we want to do is evaluate the Gini impurity for each of these splits. So for example, the first one is evaluating if the temperature is less than 9.5 and splitting on that. And if we split on temperature being less than 9.5 yes, no. Then we do the same thing. We look at if we split at that value, how does hurricane get split up? And in this case, we get the following split. And you would do, I'm not going to write all this out, but the total Gini impurity is the weighted average between Gini for temp less than 9.5 plus the Gini calculation for temp greater than or equal to 9.5, and each of those components are the same as before, which happens to be 0.429, and so that's how we get this 0.429 for the 9.5. We do that same thing for each of the possible regression values, and so now we have a series of Gini impurities. We have a Gini impurity for splitting on rainy, which is 0.405. We have a Gini impurity for splitting on humid, which is 0.214. And then we have several Gini impurities for different values to split on for the temperature. And we note that none of these Gini impurities for temperature are lower than our one for humid, and therefore our first split will be on humid, and so the root of our tree will be humid. So let's, for this example, so for deciding on the root node, since, sorry, that is not legible. Since humid has the lowest Gini impurity, humid is our root node. So now we have the first part of our tree. We know that our tree, which makes decisions and hence has the name decision tree, starts with looking at the humid variable and splits it into yes or no. And that leaves us with two sub-data sets now. We have, I'm just going to abbreviate the columns for rainy. I'll take questions after this, but rainy, humidity, temperature, and hurricane. And same for when humid is no. So rainy, humidity. And actually we don't need humidity anymore because we've already split on humidity. So really we just need rainy, temperature, and hurricane. Rainy, temperature, and hurricane. And we'll have two sub-data sets. One data set for when humid is equal to yes, and the 4 data points where that is the case are the following. 7, 18, 35, 38, hurricane, no, yes, yes, yes. And similarly, yes, rainy, no rainy, 12, 50, 83. And we have hurricane, no, no, no. So in the right case, 100% of the data points have our outcome variable, hurricane, being equal to no, so we can stop splitting here. We're done with that side. So our decision tree says that when humidity is no, hurricane is no. End of story. Make this a leaf node. In the left case, however, we didn't. We still have some hurricanes and some not hurricanes. So we do the same process, but now we just start with that mini data set. Do the same thing, evaluate the Gini impurity for the remaining variables, so rainy and different values of temperature, and split accordingly. Can anyone guess, just looking at this table, what it would probably split on, even without doing the calculation? Rainy, right, because there's rainy means hurricane, and well, yeah, it means, yeah, sorry. I read that last Y for hurricane as an N, which means it would have stopped, but that's not what it says, so yeah. Actually, we don't exactly know without splitting, but, so what we do here is the same thing. So recursively run through the same process.
So this time we would just look at the smaller table?
Yeah, but on this smaller sub data set. And you keep going until you get another situation where you split and it's all hurricane equals yes or all hurricanes equals no, and then you stop there. And basically you keep going until you've split everything. Or you can, there's hyperparameters you can set for the maximum depth if you have many variables. So you could also just stop splitting when you've split up too many times. So that is decision trees, yes. Yeah.
I don't really understand the part about the temperature and hurricane. Like, how do you even, like, what has the average got to do with the, yeah, this part. What has the average, for example, got to do with the Gini impurity?
Yeah, so the temperature is a different type of variable than rainy and humid. It's a continuous variable, so it takes numbers. So we want to basically see what would be good numbers to split on in our decision tree. And the way we decide which numbers to split on are to just take the average between different data points. Of course, you could imagine an extension where you split on.
I understand that, but what happens after you do take the average? What has that got to do with the Gini?
Then you calculate the Gini impurity for each of those potential splitting. So here we evaluated the Gini for splitting on 9.5, but we could also split on 15, we could split on 26.5. All of those splits are going to give us different Gini impurities.
Okay.
And we want to see what's the lowest Gini impurity.
So let's just say you split on 44 because it was the lowest. Would that then take temperature out, and then you would just be comparing humidity and raining?
In this case, no, because you have multiple values.
So you could just keep doing
Yeah.
temperature in there and just keep splitting on that?
Yeah, and that's actually a thing that happens in decision trees where you evaluate the same input feature when it's a continuous number multiple times, but at different splitting thresholds. Yeah.
In this case, why are we taking the mean of two numbers? Like, is that like a rule, or do
No,
we
you
take
could-
mean of three?
You can do, yeah, I mean, there's many optimizations. So this is one way to decide splitting thresholds, but you could choose other ways. Basically, you want to find different places you can split on the data set.
But not like the actual data? Like
You
I
could
can-
do the actual data as
Oh,
well.
so I can do temperature less than temperature less than 12, temperature less than 18.
Yeah, you could.
Oh, okay.
It's not going to be as, if you take averages, you're going to get more robust splitting values, but in principle, you could just take the actual values as well. It would probably end up working pretty similarly. Any other questions?
Would you scroll a little bit down?
Okay.
Oh, the other way, the other way.
Oh.
Oh, okay.
Okay, so next time we will cover random forest, which is a generalization of decision trees, where you have many decision trees together, which collectively make a forest. So that'll be on Thursday. All right, thanks.